All right, let's get started. If you're online, make sure you turn on your cameras. So today the goal is for us to finish this exercise here that we were validating the yield spatial temporal stability classes. And then I want to talk a little bit about the midterm as well. And that should be all for today. And then on Wednesday, our plans is to start doing the management zone creation. So we're going to be exploring a statistical algorithm that basically creates clusters. And in our case, those clusters are basically going to be our zones. Okay, so starting with today's finishing the stability validation exercise, if you don't have yet, go ahead and launch that project, right? So that's the 07 stability validation project. Just doing a quick rundown of what we did last time. We basically, this is the script that we merged all the layers that we have previously processed, right? So we brought in um, the spatial temporal yield stability classes. We brought in the terrain and the electroconductivity layers that had all been already cleaned, interpolated, all on the same extent. Basically, then we merged all those into one object and we exported that. And then we did some EDA, some exploratory data analysis, looking at the summaries, making a plot for each individual layer, and in the end, creating a map or a plot that included all the maps. And then we started this and spent a good chunk of time working on the validation. So creating the box plots for each one of those variables, making those plots look nice. We played around with some things that we had not seen yet. So things like changing the order of how the labels appear, and that's something that we do at the data level. So before it gets into ggplot, and then just customizing a lot of things here to get to this final box plot. And then we talked, we explored a little bit of like what was happening with different variables here, like elevation, slope, aspect, and electroconductivity at two layers, and how they were related to the different spatial temporal yield stability classes. And then we just made some visual assessment of what was high, what was low, and we just went through that process. So the next thing that we're going to do here, and maybe the last point that we left off last class was that, I mean, looking at these box plots, they do show us a distribution where we're kind of making judgments based on their distribution and also on the median, which in a box plot, the median is that black line right in, or maybe somewhere in the middle of the box itself. We're just making some comments about what was high, what was low. But as with any data, until we run a statistical analysis to give you a better idea if those differences are actually significant or not, we really don't know until we run that analysis to be able to say, yes, definitely elevation for the high stable is significantly higher than the other classes. We don't know that yet. And that's what we're going to do next today. So for us to start doing what we're going to code today in class, you do have to have everything ran above, right? So maybe if you want to come to this immediate next chunk here and click the run all above, just to make sure that we have everything going in your environment. Remember that whenever you push the run all above button, if you have left any code that has errors above, it will stop at that chunk and will not continue, even if the chunks after the one that you have error are working. So make sure that you don't leave errors lingering on your code so you can use this feature of the run all above. So really the object that you have to have for this to work is the all underscore V. Again, that's the object that has all the layers that we combined. If you just want to do a quick check if you have it, you can either inspect your environment on top and see if it's there, but probably you have a lot of objects there. So if that's not easy to find, you can just print it in any chunk. I'm just printing that here. We do want to make sure that our all underscore V has 4,032 rows. That's what it should be. As we talked about last class, if yours doesn't, then something happens and you're going to have to go back and fix whatever happened. But this is where we should be with it. So I did leave you the code to install some packages on this chunk, on the next chunk that we're going to be working with. There may be 5 packages here that you can go ahead and install. What I would recommend is that you comment off the first one, only run this, do not hit run all chunk, because that's going to create havoc in your environment. So just run that line of code, see it installing. If you don't have any issues, which I don't expect you would, just comment it off again, go to the next one, or comment it on, then go to the next one, comment it off, and install the next one. And do that until you have all 5 installed. And I'm just going to give a moment here for you to do that. While you're doing that, I just want to tell you why we're installing these packages and how we're using them next. So the package EMEANS stands for expected marginal means. It's basically a package that allows us to extract means from a model. So if you've ever heard of analysis of variance, that is the model itself. And then we use that model to extract means from that model. And EMEANS allow us to do that. MultComp and MultCompView are 2 packages that allow us to do pairwise comparisons. If you're undergrad, you may have not heard of this yet. However, if you're an undergrad going to grad school or thinking of going to grad school, you know, these topics you will run into them for sure. So it's a good, although we're not going to get into very detailed explanation of how these things work, be sure that you're going to be doing these analysis as you go into grad school. So MultComp basically allows us to do pairwise comparisons to assess if an average, a mean of a treatment, or in this case of a spatial stability class, is significantly different than another mean. So it does multiple pairwise comparisons and puts the ladders on top of those means for us to know if those means are actually different or not. So if you've ever looked at publications where you have means and you have ladders on top of those means, this is what MultComp does for us, but in an automated way. In my master's, when I was still using SAS, this process was very tedious and very prone to error. And it was basically like I was doing basically by hand, just looking, making comparisons myself. Perhaps there was a better way to do that in SAS, but I didn't know of. And so when I found out that I could automate that process and you know, don't have that to go through myself and have an algorithm do that for me, I was really excited. I guess skipping one package here on the explanation. So package cart allows us to run a analysis of variance table that uses type 3 sum of the squares instead of the default type 1 sum of the squares. You don't have to really know much about that, just that we're going to be using the ANOVA function coming from the cart package. And then lastly, we're going to be using the per package, which is part of the tidyverse. If you have installed the tidyverse, you probably already have it, but just in case, I wanted to install it again just to make sure we all had it. The per package allows us to do iteration. This is not a statistical concept, it is a programming concept. And this basically allows us to create code to do something where you write the code once and you tell the code to basically repeat that same code for multiple groups. So if you think of it, you know, let's say, so in this case here, we're basically going to do a whole bunch of steps to conduct analysis of variance that we're programming once, and then we're saying, do this for all of the variables that we have. So we don't have to be copying and pasting things and just editing code. We can just say, repeat this task multiple times. So that's what PER does for us. Okay, so after that quick rundown on what these packages do, go ahead and make sure you load them by running the library function below. So just a refresher, install packages is used just for installing. You install that once, make sure you comment it off after you install it because you're not going to be installing again. Library is something that we use every time we launch R or RStudio, where you have to load the package using the library function. Okay, so this next chunk here, I basically left all the code for you because we're going to be doing analysis of variance on an iterative way. And none of those topics are the goals of this class. If you're really interested in learning how to do ANOVA from beginning to end and how to do iteration with ANOVA, but also in for any task in R, I will be offering a data science applied to ag class next spring that we're going to go into these in more details and really slowly. I do want to maybe just walk you through a little bit so we understand what's going on here. So we're starting with all V, right? So this that data set, we have 4,000 rows. I am basically selecting out flow direction as we have already done. I am pivoting longer as we have already done as well. So if you recall, if we pivot longer, we're basically pivoting longer the field variables, right? So the ones coming from terrain and EC. So if you recall, after we pivot longer, we basically have a new column called name, as we already mentioned, that contains the previous column headings of the variables that we are pivoting. And then we have the value column, which basically holds that value only. Now, if I want to run a analysis of variance where I want to explain, I want to use, let's say, elevation to explain the ST classes. So basically being this box plot here, I want to do this, but in an analysis way where I compare the medians of these box plots. I'm basically going to run a model where I have, so value here being the value for a given, let's say, elevation value explained by ST class. However, to do this, we do have to create groups in a very different way from what we've done before. So we do a group by name to say that we want to create data sets that contain one of the name or one of the variables here only. And then we nest. You have not seen this function yet. I'm just going to show you what that does. So if you recall, doing the group by itself doesn't change the data, right? So after pivoting, we have like 20,000 or so rows. When we group by, that remains the same. We just behind the scenes create a grouping structure, but that does not change number of rows. And now I want to nest by that group variable. So this column names again contains all the field data. And if I nest by it, let me just run this so we can see. I just ran, saved on ANOVAs, and I will print it. When we nest by it, this is what we end up with. It is a new concept that for me, when I just learned this, it took me a while to make sense because it's not very intuitive. But basically here, we group by and nested by name. So it took each one of the levels of name and put under this column name. And then it created a new column for us called data. And this column basically has a data set that is related to only that variable. And it's really, the weird concept here is that this column is a column where each cell is not a single value anymore, is actually a whole data frame. So it is data frames inside of a data frame. It is a weird concept, but that's how iteration, one of the ways that we can do iteration in R. So just so you know, or just so you can see, so that at this point, I save this to this object called ANOVAs. If I use the $ to call one of the columns, right? I'm going to call data. I'm not going to run this because this is going to print all these 4 data sets or 5 data sets, which I don't want. I just want to print one of them so you can see. So if I sample this by using the bracket notation, I'm basically doing ANOVAs data set, data column, and the first value of that column. So if I run this, I'm going to print this cell right here, which again is a data frame in itself. So if I run that, this is what we get. So we go back to 4032 data rows because now we only have all the data for elevation. And we know it is elevation because elevation is the first value on the column name, right? So if we were to do name here instead of data, that would have returned elevation, but we want to see the data for that variable. So I use the column data. This is what we see. And if we just browse to the side here, we don't have anymore in this data the column name because that has been nested out when we did the nest, but we still have this column called value. And this column called value for this first data frame is only elevation. But if we were to do the second data frame, it would be, the value would be for the other variable, which I think is slope. The second one I think is slope, and so on. So basically we created groups and we nested by those groups and created data frames that are only referring that the value. So all of these data have a column called value. However, that even though the heading name is the same, those values only refer to this variable on the outside here. I know it's kind of complicated and I don't really expect you to fully understand, but I just wanted to give you some intuition of what we're doing. So once now we have a column called data where the data refers to each one of those variables, we can we can do a whole bunch of things. So the first thing that I want to do is run a linear model that we use the function lm, where for each one of those data cells, it's going to run the formula value explained by st class. So st class is still the same, is not changing. The value now is changing according to what data set we're looking at. So if I comment off my pipe right here and just run until here, I want to show you what happens with the object ANOVAs. If we print it, now we have a new column. That this new column is a linear model that in this case, it's analysis of variance, ANOVA model, that each one of these models is referring to that specific data set on that row that is referred to that name variable that we have on this column. So now we're basically creating new columns where the cell value is not a single value anymore. It's different objects. So let's say if I wanted to have some idea of the model that was run for elevation, I could use the $, go on mod, and then sample that, or take that one only by doing the one. So this is basically just how it would look like. So we have an intercept and then some different values for different classes. So the workflow of an ANOVA, so remember, what I'm showing you is code to do ANOVA, which is probably something new for you, but on an iterative way, which is very new for you. So if you were to do an ANOVA for only one variable, you could have skipped, it could have been a lot simpler because you wouldn't have to have the iteration structure behind it. But this is basically what we would do. So we will run a linear model here that in this case is an ANOVA. Next, we extract the ANOVA table. So let me run until here and show you. If we run until here, now we have a new column that's going to be called ANOVA. Let me print the object ANOVAs so you can see. Now we have this new column called ANOVA. And if I sample just the first one to show you, this is an ANOVA table. So if you are in grad school, you probably have seen something like this, where we have the source of variation. In this case, is just st class, because that's the model that we ran above here, is only st class. And then we have sum of squares, degrees of freedom, an f value, and a p value. So the p value here, if it is below 0.05, basically means it's significant. So the effect of st class on this first model, which was for elevation, is highly significant. If I wanted to print all the ANOVA tables for all the variables, I just do this. I remove the indexing and it just runs for all of them. So for the first one here was elevation, highly significant. The second one was slope, highly significant, and so on. And if we just look at the p-values, we see they're all highly significant, meaning that at least one of those means of st class was different from the others for a given plot that we look here. So at least one of those means are different from the other based on that p-value on that ANOVA. So on an ANOVA workflow, so we run the model, we extract the ANOVA table, we look at that ANOVA table to decide if we should go ahead and extract means and do pairwise comparisons. In this case, since all p-values were significant, we decided that we should do that for all variables. So I'm going to let the workflow continue. On this next variable that I'm creating on this data frame, I'm calling CLD for, I think it's the short name for like compact ladder display, which basically first is extracting the ST class means and then doing pairwise comparisons using the CLD function. And then just doing some wrangling on the go here. Don't really have to know much about it. So if I come here and I add a pipe right there just to stop the flow here so I can show you what CLD is, I'm going to run this. I'm going to come here and just print this ANOVA's object again so we can see that new column now. And again, after you nest and you use the map function, so we're using map, that's basically the function that allows us to do iteration. So we say do ANOVA function here, but for each one of the data that you see on that nested data set, that the map function is what is doing that iteration for us. So now we have this column called CLD. So if I get CLD for the first elements, which would be for elevation. So if I use $ CLD and use the brackets to get the first, so opening up this data here, which is the elevation one related, if I just print it, this is what I get. So I get the different classes and they're coming because ST class was again in our model here. So that's why we have ST class here. We have the EM mean, that's the expected marginal mean coming from the model for each one of the classes. So this EM mean here in this case is elevation, right? Because we're printing the number one, which was elevation. So 15 going, so high stable had the highest elevation, at least numerical at this point, highest elevation numerical, about 51 feet, and the lowest one was unstable, about 46.6 feet. It gives us a standard error, gives degrees of freedom. It gives us the lower and upper confidence level of that mean that's calculated based on the model. But really what I'm after here is the ST class, the EM mean, and the ladder. So these are the letters. So if you have not seen this in your career yet, if you're doing your undergrad and you have not seen ANOVA explanation, a very, very quick introduction here would be if you look at a mean and you look at the letters. So if two means share a common letter, it means they're not different at a significant level of 5% in this case. So for example, the two last means here, they are for the low stable and unstable classes. These are their means, and both of them have C's. So they do not have significantly different elevation between them, but they are both of them are significantly lower than the second class here, which was medium stable, which was also significantly different from the first letter here, which was the high stable. So that's how we would interpret the letter separation from any analysis of variance. Okay, so this was a very quick rundown on ANOVA, and especially on an iterative ANOVA for 5 different variables at the same time. My goal with all this chunk here was basically, I wanted this CLD where I had the name, like the variable that we're using to explain using ST class, the mean coming from the model, so the EM mean column and the letter separation column. Now, how can I plot this in ggplot if what I need is actually in a data frame, but it's then inside of another data frame inside of the data frame. So it's kind of a weird way of thinking of this. So now that we nest to make iteration. So now we've finished doing the iteration where we fit an ANOVA model, we extracted the ANOVA table, extracted the means and pairwise comparison letters. Now I want to unnest, and I really want to unnest only this column here. I do not care about the data column or the model column or the ANOVA table column. I only want this one because I'm after the letters. So I basically come here and use a function unnest, and I say unnest and then which column I want to unnest. I'm just going to comment this off so you can see. So remember that up until this pipe, up until here, this is how the data looks like. It's still nested, right? So now if I let it flow through unnest and stop there, now it's basically going to take that CLD column and open it up and bring into the main level of the data. So now look, notice that we went from five rows to 20. And the reason for that is that for each one of the elevation or each one of the name variables, so in this case here, the first 4 are for elevation, it unnested the CLD object. So now we have here the EM means, we have the standard error, degrees of freedom, confidence levels, and the letters. And then we have that, so 4 times for elevation because we have 4 ST classes, and then 4 times for slope, and then 4 times for aspect, and so on. So we basically took that column CLD and we unnested it. We reopened that into the main level of the data. And then I'm just ungrouping here because we did a group by before, so I'm just ungrouping, and I'm just changing the levels again of the terrain variables. They are still under this column called name, and I'm just changing the levels so they appear in this order when we plot them, which is something we have already done, so you're already familiar with this part at least. Okay, so if, I left you all the code because I don't expect you to learn how to do all this. I just wanted you to understand what is going on in case you, I don't know, for some reason you want to explore this further on your own. So if you make sure you don't have any of the block or any of the pipes commented off, like I was doing, so make sure you don't have any of that, and just go ahead and run the entire chunk. Now make sure that your install packages are commented off, so you have a hashtag in front of them. You can just go ahead and run the entire chunk. And if you did install the packages, and if I was able to tell you which ones you needed to install properly, the chunk should run all right. Is anyone having issues to run the chunk? We have to have the chunk running to get to the final step. Okay, I don't hear anything. So I'm taking that as everyone was able to run it. So really what I need from this object ANOVAs now is really the name column. I do not need data mod ANOVA. I need ST class, I need EMEan, and I need the letter column, because that's going to allow me to place that letter on the plots, on this plot here, so we can have letters here and really be able to look at the box plots and then for sure know what is significantly different and what's not. Okay, so assuming that everyone was able to run that chunk that I left you, let's someone online has a question?
Yes, I got an error in mutate.
Where was the error? Can you repeat that?
Okay, here I have an error, and it's an error in mutate.
In mutate. Okay, so we're using mutates to create the different columns, right? So if you did not change the code that I sent you, the code itself should be working. So there's nothing to change in the code if you did not change on your side after I sent you. The possibility of the mutates not working perhaps is because you didn't load or install the packages. So in this first mutate, we're using the function lm. So that comes from base R. Everyone should already have that by default. The second mutate, we're using the function ANOVA uppercase A, which comes from package car. So make sure you have that installed and loaded. The third mutate, we're using functions EMEans, which come from EMEan package, and function CLD, which comes from multi-comp package. However, when you're installing multi-comp, you also have to install multi-comp view for them to work properly. and then we're using the factor function of the last mutate, which is also base R, so there's no package loading need for that. So if you're getting an error on a mutate and assuming the code is the same as I sent you, I wouldn't just make sure you have installed and loaded the proper packages. Let me see, someone has a comment. Maybe it's because of the name of the column, like, oh, okay. Yeah, so Kriti had a great point. So if for some reason you did not name your your ST class column, so if you print all V should have a column called ST class. So all V is our like merged or joined data set before getting to all those details that should have 4,032 rows. You should have a class called ST class. So what Kriti is saying is if your column here is not called ST class, then you don't have this column here to refer to. And I would highly recommend that you have a column called ST class, because otherwise it's not gonna work in the next chunk. Were you able to find the solution?
I'm installing the packages again to make sure that I did it properly.
Okay. Yeah, I'm gonna give you a moment. And yeah, let me know if you need help or. Okay, so here's what I want to do with code. I basically want to take this plot that we have already created and add the letters to each one of those box plots for each one of those variables on the plot. So we basically already have most of the code to do this, right? I mean, we have the code that produced what we're seeing right here. So I do want to invite you to come up on your code, go on the chunk that is called box plots, where we created this plot here. Just go ahead and copy that. So you can just copy the entire thing, starting on all V and ending at that last parentheses. You're gonna come to the chunk after the ANOVA chunk that we just did now, and you're going to paste that right there. So if you do run this, it should still be the same plot as before, right? Because we just copied and pasted the code, so it should be the same as we have already developed. Now I want to show you how can we add the letters to these plots. So in my early days of using SAS, I would add the letters by hand. So I would have it could even be like I have produced the table with the means and the letters on R or maybe on SAS at that point. But then I would bring this into, I don't know, PowerPoint. I would, see what was the letter for elevation and low stable, and it would put the letter right there manually, which is pretty tedious, prone to error. And I just discourage that, I guess, if you know how to do differently. So I want to show you here, how can we add the letters, right, on each one of these box plots and right at the mean of that box plot. I don't think we've used the function that we're going to need next yet, but I still want to ask, does anyone have any thoughts of which function we would use to add letters to a plot? So one way of kind of figuring that out is you could come here and just do like a geom. Oh, someone had a comment?
Do we use theme function?
Say that again.
Do we use theme?
TM, you say?
No, theme function, THEME, theme or theme, how do we call it?
Oh, yeah, I see what you're saying. No, so it's actually not through theme. Yeah, I don't think that's something that we would do through theme. I'm just thinking of like previous ways I use. It would be a geom, right? So remember that we're gonna have to be mapping that text or that label to variables. So it's going to have to be through a geom. So one way that I would, of course, like we have not used this yet in class, and if you have not used R before this class, you may not have been exposed to this. So I wouldn't expect you to know necessarily, but how could you find out, right? One way, I guess the first way would be Googling how to add text on a ggplot in R. That would be the first way. If you let's say that you kind of knew the function, but you forgot the name, you know that it starts with geom underscore something. You could come here and do geom underscore hit tab, and you could look at the options. You could also look into the ggplot2 cheat sheet. That's another resource that you could also find it. So there is a function called geom underscore text, and there's one called geom underscore label. They're very similar. We're going to be using the geom underscore label one. So if we do that, we're using that geom. Because the labels and the means that we need to add are coming from a different data set or a different object, right? So all the plot that we develop here is all based on all-v. Now, the object that we have the labels in is what we created up here. So is the object called ANOVAs. And remember that now ANOVAs, if I just print it so you can see, should have 20 rows where we have the columns we really need are name, EMEAN, and letter. That's all. So what we need now to make the letters on that plot is this object ANOVAs. Every time you can always plot different data on the same plot. So we have not done much of that yet. We have only started with one data set and then creating the flow for that to create a plot for that data only. In this case here, everything is on this plot is based on all-v except the labels. So the labels are going to be based on a different data set. So we can specify that and say data equals ANOVAs, right? That's the object that we did all the work above on the chunk above. We add a comma. I want to hit return just to break the code. And because the labels are going to be changing according to the name column, we need to specify some things within the AES function. So go ahead and call AES. Now, the X column, I guess we can try to see, but I don't think we have to specify the X column itself, because the name of the X data is the same in both all-v and ANOVAs. Is named the same as ASTI class. So we don't even need to say X equals ASTI class here, because that is coming already from above here. However, the Y value that we want to put the letters is not the same name, right? So on the all-v, it's called value. On the data, I want to place the letter on the mean value. And the mean value is in the column, if I just print here ANOVAs again, that mean value is under the column EMEAN. So I do have to say here Y equals EMEAN, just like that. And then this geom label especially has an extra argument that other geoms don't, which is called label. So you can, still inside AES, and after saying Y equals EMEAN, add a comment. I want to break code just to make it easier to see. And there is an argument called label. So label is where you say which is the column name on that data set that has the labels you want to add. In our case, that is on the column called letter, right? So we just say label equals letter. Make sure you close your parentheses for the AES. Make sure you close the parentheses for geom label. And don't forget to add a plus, so it connects with the remaining of the plot. Now, if you run it, let's see, there we go. It basically knows exactly where to put the letters. So is on the x-axis is putting on the ASTI class using that column. On the y-axis, it knows where to place the labels because it's placing right at the mean of that box plot, pretty much, because that's what we said, that's what we told it. And then it's adding the letter to each one of those box plots as well. if the making of this, of the creation of the letters and going through all that is a little bit too confusing, don't worry. I guess this was my goal, was just to get this through and then be able to have this map where now we have the letters, right? So now we can use the letters to say this was the highest and it was significantly different from this one, or it was not significantly different from this one because they share a common letter. What was that? Can you read me the error? I can try to help you afterwards. I just want to get to this part here. Okay, so we are going to basically go through this exercise here together. I'm going to be asking all of you, because we have lots of questions here. Yes.
Having some errors in Tifton. Could you let us see your code again?
Yeah. So the only thing, so I copied the code that we did previously. The only thing I changed was to add this. So you just got to you do have to say data equals ANOVAs. If you just give ANOVA without saying the argument data first, it may not work. Remember that y equals EMEAN and label equals letter has to be within AES. And then don't forget to add the plus at the end of geom label.
I'll tell you, I'm doing it the way, like, I got an error, and then I did it the way you said, just run it chunks at a time. And everything up to that plus right there in the highlighted area worked. But anything at faucet wrap on, like, you know, if I run it whole, that's the error. But if I like just highlight after that chunk we wrote up, it works fine. And that's why I'm trying to understand where my error is. What's the error? What's the error?
You do have the plus at the end?
Yes, sir.
Okay. Well, I don't really know what.
If I highlight there up, it works.
But I can help both you and Dennis after class. That's okay.
Thank you.
All right. Okay, so let's now finally get to define here. So I will be asking all and each of you to help me at some point. So let's first define the high stable areas, right? So if so high stable is the orange one, at least in my plot is the orange one, right? So if you look at the elevation plot and you had to say high stable had the highest, the lowest, or maybe, and this, remember, now we're talking highest, lowest, not only based on the box plot and how it looks, but also on the ladder. So I'll do the first one here just to show you, or just to give you some help. So since we're defining high stable, I'll look, and this is elevation, I will look on the elevation plot. The high stable is this one. High stable has the A letter and nothing else has A, right? So B, C, C. So high stable had the highest elevation, right? Significantly highest elevation, but I'm just gonna skip the word significant, but I do want you to keep that in mind. So go ahead and write this down as well. So elevation has, or high stable had the highest elevation. Okay, let's just keep going down the other plots now. What about slope? Amrinder, what would you say here that high stable is in relation to slope? So you think that, wait, we're looking at high stable, right? So I want to say high stable has highest or lowest.
Similar to the unstable.
But is that highest or lowest or intermediate? Lowest, right? Because we have lowest and they have C. So in this case, A is going to be highest and then C or D is going to be lowest. So slope has the lowest slope. Aspect. What do you think, Sandesh? So I'm trying to characterize the high stable areas, right? So I'm looking at, let's say, high stable on the elevation map, it has an A and everything else does not have A. So for elevation, high stable is the highest, significantly highest. So we're just going through characterizing high stable, going through each one of the plots. Okay, Sandesh, what about aspect? Highest, right? Because it has A and everything else is either B or C. So it has highest aspect. What about ECA shallow, Peter? How would you characterize high stable? Like intermediate, right? So it's like, it's not highest, but it's also not the lowest. So let's say intermediate. What about ECA deep? What do you think, Dennis? How would you characterize high stable? Highest, right? Because it has an A and everything else is either B or C. Okay, awesome. Now let's do the same, but for low stable areas at this time. So I'm just gonna run everyone here in Athens and then we'll go online. David, how would you characterize low stable with elevation? Lowest, right? Because it has a C. I mean, also unstable has a C, but we can refer to it as lowest. So low stable has lowest elevation. Trip, what do you think about slope and the low stable?
Lowest. Slope, medium, intermediate.
Yeah, intermediate, right? Because it's B, and then we had a C for the other two classes there. So for slope would be intermediate. Alexis, what do you think about aspect and low stable? Lowest, right? Because it has C. It does share a C with unstable, but they're both lowest. So lowest on aspect. Duster, what do you think about low stable and ECA shallow?
Lowest.
Lowest, right? All right, let's go online now because we ran out of people here in Athens. Let's go to maybe Tifton first. So let's see. Is Austin there?
Yes, sir.
Austin, how would you characterize low stable areas in relation to ECA deep? So looking at this plot here.
Lowest.
Lowest, right? Because it has a C and it shares a C with unstable, but both of them are lowest. Yep. All right, so we finished characterizing high stable and low stable. Let's do that for unstable areas now. So if we go unstable in elevation, is Ethan in Tifton?
Hey, he just stepped out for a bathroom break real quick. He'll be right back.
Okay, is Miller in Tifton?
Yes.
Okay, Miller, how would you characterize unstable in relation to elevation?
Lowest.
Lowest, right?
Yes, sir.
I agree. Oh, I think I had the order here. So I'm just gonna bring slope and aspect to be after elevation. Okay, so how would you, well, let's see, let's go with Emma. Emma, how would you characterize unstable in relation to slope?
The lowest.
Lowest, right? All right. Now, let's see, I have here Anish in my next. Anish, what do you think about unstable in relation to aspect?
Aspect lowest.
Lowest, right? Yep, I agree. Okay, next I have Kriti on my screen. Kriti, what do you think about unstable and ECA shallow?
Lowest.
Sorry, can you say that again?
Lowest.
Lowest, right? Yep, I agree. So I'm just gonna say lowest as well. And then finally, unstable in relation to ECA deep. Next one I have here is Sekar. What do you think, Sekar?
It's lowest.
Lowest, right? I agree. Awesome. Oops. All right, I guess we ran out of questions here, but thanks for everyone that helped me out. And so I do have a quiz here, but I know we're running out of time. Let's do this. If you can do the quiz now and answer these questions here and send me by email before you leave, I think you should take maybe 5 minutes max. So we have like 1 minute left on the clock. If you don't have something you have to run to and you can complete in the next 5 minutes, do make this quiz here and answer this to me. if you don't do in class, I would ask you to have as an assignment. It's going to be graded as a quiz, but if you cannot stay for the next extra 5 minutes, I don't want to keep you here, but you have to send me your answers before next class. So if you do have 5 minutes to spare here, go ahead and answer this quiz in class. If you have to leave, do that, but make sure you send me these answers by tonight. And what I'm asking here is basically based on the answers above. So if you look at how we characterize high stable, how we characterize low stable and unstable, based on those, how would you explain why high stable areas are high and stable? And what is your hypothesis of why that's happening? So let's say I look here and I see that high stable has all these features of like highest elevation, lowest slope, and so on. What would be your hypothesis to explain why that is the case? Why these variables are making these areas high stable? That's the first question. The second question is the same, but in relation to low stable. So why do you think the low stable areas in comparison have these features? What is your hypothesis for that? And then what perhaps is going to be the most challenging one to think about is to explain the unstable areas. So remember that unstable means that, let's just quickly talk about it, right? So unstable has a very high CV, which means that some years it may have very high yields, in other years may have very low yields. So what is it about year differences? Probably related to weather and how weather is interacting with these features that we have measured as far as terrain and EC. And what is your hypothesis of why these features are creating unstable areas? So those are my 3 questions. If you can answer them in the next 5 minutes, please do so. If you do have to leave, I respect that, but then make sure you respond to me by tonight.